Good morning, friends. Today we are going to design a Cmos NAND gate and NOR gate using 120 nanometer technology for capacity load of 0.01 picofarad. Now, what is the aim of this? Is the second practical of our subject VLSI design and technology. The aim of this practical is to design, prepare, and simulate layout of CMOS NAND and NOR logic gates using the CMOS bits. For this purpose, we have to select the technology point. Means we are going to use the using the technology 0.12 micrometer, means 120 nanometer technology for capacitive load 0.01 picofarad. And finally, we have to take the reading for rise time and fall time, area, and power consumption of our design. The learning objective of this practical is to design and verify layout of CMOS NAND and NOR logic gates for specific technology, means for 120 nanometer technology for the load capacitors of 0.01 picofarad. We can you can also design this layout for different capacitive load also, because our ultimate aim is to observe the capacitance load effect on the rise time and fall time, as well as power consumption and area. Okay, for the different technology. Second objective is, our aim is to understand the microwin software for development of layouts of CMOS signals. How we can use this software, how we can prepare the layout for different technology by using the different lambda rules. Okay, this is the second objective. Third is, we have to calculate and observe the rise time and fall time, power consumption and area for the CMOS NAND and NOR logic gates, and we have to conclude that what is the effect of load capacitance on rise time and fall time, power consumption and area for particular technology. Okay, now the outcome after designing and preparing the layout for CMOS NAND and NOR gate, the outcome of this practical is you are finally you are going to able to perform this practical. You are going to able to design and verify the layout of CMOS NAND and NOR logic gates for different technology, assuming the load capacitors. The requirement for this is you have to require desktop PC or laptop and microwin software. Here we are going to using the microwin 3.1 full version software. Now you are familiar with the NAND and NOR gate. These are the basically universal gates. Okay. Now any gate we can design using the NAND gate also. Now let's see what is the circuit diagram of these gates. 1 minute. I will open. Okay. Okay, this is the schematic of CMOS NAND gate. Okay, now as we are familiar, what is the symbol of NAND gate? Okay, 1 minute. I will show you the diagram. Class materials. I will open the PPT. Okay, this is the symbol of CMOS NAND gate. It has two input and one output. Now here we are going to reason the two input NAND gate. Now the functionality of NAND gate design is, when both input are 1, my output is 0, and when any one input is 0, my output is logic 1. Okay, means when both inputs are 1, output is always 0. It will exactly work as opposite to the AND gate. Okay, now from this truth table we have designed this K-map, and from this K-map we have obtained the equations. From that we can design the CMOS NAND gate. Now this CMOS NAND gate consists of two networks, pull-up network and pull-down network. In pull-down network we are using the N-channel MOSFET devices. As NAND gate equation is Y is equal to A dot B bar. Now, if we simplify this equation for two in pull down network, two n-channel MOSFETs are connected in series, and opposite to that in pull up network, because p channel exactly works as a opposite to the n-channel MOSFETs. Hence, in pull up network, two p channel MOSFETs are connected in parallel way. Okay, means you can obtain the fair value of the NAND gate, or correct value, proper value. Hence, here in pull-up network, source source of p-channel MOSFETs are connected to the VDD, and in pull-down network, source of second n-channel MOSFETs is connected to the ground. And here, drain of p-channel MOSFETs M3 and M4 and n-channel MOSFET M2, these all drains are connected together and output is taken from this drain. Okay, and this is the circuit diagram of CMOS NAND gate. Now we will execute, we will draw the layout using the micro:INT software. Now open the folder micro:INT 3.14, open the system folder, and in that micro:INT 3.1 executable file you can see. This is the application file, and double click on that file. Okay, now this is, now here you have to draw your layout. Before going to draw the layout, first aim is select the foundry, file, select foundry, then here point 112 rule file, 0.012. Okay, open this file. Here 5 lambda, here you on left hand side you can see the distance. 5 lambda is equal to 0.300 micrometer. Okay, if you zoom out this, okay, here you can observe the, okay, 1 lambda distance also. Okay, 1 lambda. 1 lambda is equal to 0.060 micrometer. Means now we have reducing the scale. Okay, means 1 lambda. The distance between the two dots is now 1 lambda, and it is equal to 0.060 micrometer. And this distance is variable depending on the quantity. For 120 nanometer, the distance is 0.06 micrometer. If we reducing the technology, this distance is again reducing. Remember this point. Now, as for NAND gate, okay, pull-up network consists of two p-channel MOSFETs, okay, and pull-down network consists of two n-channel MOSFETs. Okay. Now, first of all, we will draw the pull-up network. Means we have to draw the n-well first of all. Okay, I will again delete this. Okay, after that, on downward side, n plus diffusion, because by default PVL is present. Okay, first of all, for pull-up network we have drawn the n well, and in that n well we have to draw the p plus diffusion material. Okay, again you can check the DRC. Okay, again while drawing this design you have to remember, you have to follow the lambda rules, which are known as design rules. Means the width and length of this n well, the distance between this n plus diffusion material and n well, the width of n well, similarly width of n plus diffusion, all these rules you have to satisfy. Okay, if you don't satisfy the rule, the DRC will show you the error. Now this is the n plus diffusion material. Okay, again I will check the DRC, it's okay. Then here how many gates are required? Here two gates, because two polysilicon material required, because two inputs we are going to provide. It is a two input NAND gate. Hence to connect the two input we have to draw the two polysilicon layer here. This is the first polysilicon layer I will draw, and this is the second. Keep the safe distance, means to follow the lambda rules. Okay, I will drag here. Stretch and move tool you can use to drag. Okay, again check the DRC. Now you have to make the connections. How to make the connections? Here you have to short. Here you have to short the drain or source of both P channel MOSFETs together and connect to the VDD. Means you have to short the sources also, and you have to short the drain also to connect to the output. Okay. Again here I will consider the outer side is a source. Okay, I will check the DRC to see. Okay, correct. Now here I have to put the contact. Okay, now contact is going outside. Hence, what I will do, I will drag this and increase the length. Okay, put the P plus contact. Okay. Now next connection is we have shorted the both sources. Again drain. Okay. Now as this is the source, then by default this is the remaining second part is the drain. Again this is source, then it means drain is a common area here. No need to short, means it is already shorted here. Okay, and from here we have to take the output. Okay, now again I will increase the width. Okay, put the contact here, DNP contact. Okay, again I will check the DRC. Okay, now some design rules show the errors. The spacing between the metal is less than 4 lambda, means this distance should be minimum 4 lambda. Now I will increase this distance size in this way. Okay, again DRC. Okay, again the distance is less than 4 lambda. Okay, correct. Okay, now at downward side, first of all you will see the source of second NMOS is connected to the ground. Again, second source and drain, source drain of second and source of first is shorted together, and after that output is taken from the drain of first. Okay, then what we will do? Okay, the output is connected to the, okay, this is, suppose this is the source of second. Okay, I will connect this. Okay, then source, then drain and source are shorted, and from here output is taken, means we have to select the output from here. First of all, I will stretch this device. Okay, clear. After that, put the contact and contact here. Okay, now this here contact, I have to increase the size. Okay, put the contact here again. Okay, now everything is completed. Source is connected to the ground. This source and this drain is shorted, and from drain we have taken the output is the drain of both P channel MOSFETs is connected to the drain of first. Okay, now connect VDD and supply. VDD you have to connect here. Okay, both sources are connected to the VDD. Again, VDD is given to the veil also to avoid the floating, means to complete the circuit. And ground is connected here. Okay, now we have to apply the input here. First input. Okay, this is the first input. Input, I will say this is the input A. Okay, now again this is the input A assigned, and after that provide the second input. Now remember, while applying the second input B, you have to change the rise time for time, because if we remain same rise time and for time, then we are not applying the different combinations of input, because as frequency is same, we cannot apply the variable combinations. Since to we have to make either slower or faster. Okay, I will make slower and assign. Okay, and finally output is taken from common region here. This is output AUT POT. Okay, completed. Okay, completed. Save this again, once again DRC, no error, and then simulate the design. Okay, now we will start from here. First, when both input are 1, my output is 0. Okay, and for any other 0 input, when anyone is 0 input, my output is 0. Clear? Okay, 0 first combination, 0 1, my output is 1. 1 0 1 1, my output is 0. 0 1, my output is 1. Again 1 1 0, means when both inputs are high, 1 1, output should be 0. You can see the truth table here. Okay, 1 minute. Okay, truth table shows when both inputs are high, output is 0, or any combinations. Other means anyone is 0, output is 1. Here you can show the same way. Okay, 1 1 0 0 1 1 1 1 0 0 0 0 0 1 1 0 1 0 0 1 1 0 1, means any combination of 0 input. Here either this is 0 or either this is 0. Okay, this both are 0, then any one is 0. Here both are 1, output is 0, means your output, you will your functionality of NAND gate is verified, means whatever you have designed, it is correct. Now our aim is to take the reading. Again, to take the reading, first of all you have to apply the capacitive load of, what is our statement? Statement is you have to apply the capacitive load of 0.01 picofarad. Now at the output sides you have to correct the capacitive load of 0.01 picofarad. Okay, it is a 0.01 by default. Okay, select this, save, and again run. Again I will minimize the scale here, 2 nanosecond, sorry, 10 nanosecond. Here you can see, because of capacitive load applied at the output, it will not go directly. Okay, I will increase the capacitive value. So decrease the value. What will happen? We will see. Okay. Okay, 0.001 picofarad. Here you can observe the capacitance value is higher. It will not go to the 0. Then I will receive this. Okay, in this way you can verify the output. So for high capacitance value, first of all you have to apply without capacitance. You have to simulate the device, and after applying the capacitance you can see the effect of applying effect of capacitance on the rise time, fall time. Okay. Now you can take the reading. The rise time is when the output waveform switches from logic 0 to logic 1, it is a 14 picosecond. When it switches from logic 1 to logic 0, fall time is 13 picosecond. Okay. After that, power consumption is 0.779 microwatt, and final one reading is remaining, which is nothing but the measured distance, means you have to measure the area. Okay. Here you can see the scale. The width is 2.700 micrometer, and length is 3.06 micrometer. Means area is near about 3 into 2, near about 6, near about 6.75 micrometer square, near about. Okay, you can multiply this both. You can multiply the length and width and find out the area. In this way you can design the Cmos NAND gate using 120 nanometer technology and assuming the load capacitance. Okay, good. Thank you. Okay. Now second design. Okay. Second gate you have to design is Cmos NOR gate. Okay, Cmos NOR gate. Now what is the change in the Cmos NOR gate? All of you familiar with the Cmos or NOR gate? What is the truth table for Cmos NOR gate? We will see if it is available with us. Otherwise I will told you. Okay, this is the Cmos NOR gate. In Cmos NOR gate, it has again two input and one output, and truth table shows that when both inputs are 0, output is logic 1, and when any one input is high, output is logic 0. Means it will work exactly opposite to the NAND gate. For NAND gate, what happens when both inputs are 1? When both inputs are 1, output is 0, but for any another combination, output is 1. Means here is for when any one input is high. When any one input is high, my output is logic 0. And when both inputs are 0, it will logic 1. Now OR gate means NOR gate is exactly opposite of OR gate. Okay. In OR gate, when any one input is high, my output is logic 1, and when both inputs are 0, output is logic 0. But NOR gate, when any one input is high, my output is logic 0, and when both inputs are 0, my output is logic 1. Okay. Now after by using this two table, we have put this value in the K maps, and from K map we obtain the equation. Equation is equal to y is equal to a plus b bar, and finally we have designed the CMOS circuit. In CMOS circuit, we can show that in pull down network both n channel MOSFETs are connected in parallel. Okay, and in opposite to the pull up network, both p channel MOSFETs are connected in series. Means the circuit is exactly opposite to the NAND gate. Okay, now here in pull up network, the source of M3 is connected to the VDD, and drain of M3 is connected to the source of M4, and again source drain of M4 is connected to the drain of M1 and M2, and output is taken. And finally source of M1 and M2 are connected to the ground. In this way you have to design. Means here we will require the two polysilicon material to apply the two inputs. Okay, let's start this. How to design again? Open the micro wind. Okay, then to draw the p channel MOSFETs, first of all draw the n well. In n well, again you have to draw the p channel. Now while drawing this layout, first of all remember this layout. At start you are not familiar with the design rules, then at every step there may be the errors. Okay, but every times here if I decrease the distance between this p plus diffusion material and n well, what happens? I will show you, because this is very important to understand the lambda rules. People are going to draw this. Okay, now here DRC. DRC shows that the distance, the extra annual surrounding diffusion P is less than 6 lambda. Means the distance between this annual edge and the P plus diffusion should be minimum 6 lambda. Okay. Okay, again I will check the DRC. Okay, now it is correct. I will zoom out this. After that you have to draw here N plus diffusion material. Okay, then draw the polysilicon material. Okay, drag this. Okay, again I will check the DRC. Correct. Now to make the connections, first of all understand the circuit. Here first of all, source of first P channel MOSFET is connected to the VDD. After that drain and the source is shorted. And after the from drain you have to take the out. Okay. Then take the metal one. Here I will connect the source to the VDD. Okay, then drain and the source is shorted, and from this drain we have to take the output. Okay, now this drain is shorted to the drain of both P channel MOSFETs. Means we have to short this. Again I will do the connection. Okay, now I have shorted these both drains. Somewhat connections is remaining. Okay, clear. After that we have to connect this source, then drain source shorted, and this drain is connected to this drain. Then I have to again select the metal one and connect this device. Okay, I will make in this line. Okay, right. And finally, one connection is remaining. Both source of n channel MOSFETs are connected to the ground. Now this we have to connect to the ground by using metal one. Okay, first of all check the DRC. Okay, no error. Save the device and then put the contact. On upper side we have to put the contact P to N channel, P to metal 1, and lower side N to metal 1. Okay. Again I will check the DRC. Correct. After that, okay, first of all see whether we have selected the foundry 012. Okay, selected. Okay. After that, we have to make the connections for VDD to NVL also, and ground. Okay. And apply the input through clock. This is clock A is input A. While applying the input B, now we will increase the, it will make faster so that all combinations of input we will get. Okay, and finally before going to apply the output, okay, apply the output here. Okay, select this. Okay. Now everything is fine and we will simulate the device. Okay, now here what happens, we have not make the faster, means both we will get the two combinations of input also, because frequency of input A and input B are same, hence we are not getting the all combinations of the input. Now to solve this problem, what we can do, we can increase the faster the device, again faster. Okay, assign, save. Okay, here you can observe the all combinations of the input. Now here you can also calculate the frequency by selecting. Okay. At this stage I will disable this. Okay, what happens? 10 nanosecond I will select. 1 minute, 2 nanosecond. Okay. If we select the 5 nanosecond. Okay. Now we will see for all combinations. So starting with this, when input A is 0 and input B is 0. Okay. What is the two table set? Two table set, when both inputs are 0, output should be 1. 0, 0, output is 1. And for another three combination, 0, 1, 0, 1, 0, 0, 1, 1, 0. Again 0, 0, 1. Means functionality of the NOR gate is verified. Now you have to take the reading. Here power is 2.743 microwatt. Okay. Rise time and fall time also shown on the waveform also. Itself is a 20 picosecond, near about 20 picosecond. Fall time is near about 0, but rise time is 20 picosecond. Okay. Okay. And third, you have to calculate the area of the design. First of all, I will zoom out this and then calculate the area to select the scale. Okay, now what the scale says? Scale says the width is 3.9 micrometer and length is 3.84 micrometer. Means near about 3.9, 3.44 into 4, near about 16 micrometer square is the area. In this way, you have to take the reading. Okay. Now you have to apply the capacitive load, and again verify the output. Okay. Again, I will delete this. Okay, a minute. Okay. Okay. Now apply the capacitance. Add the virtual capacitance at the output. Okay. Value again we will add the small capacitance 0.001 picofarad. Okay, 0.001 picofarad. Okay. After applying this, again save the design and again simulate the. Okay, now here you can observe the adding the small capacitance. Rise time is smaller from 20 picosecond, it will increase to the 22 picosecond. Okay, if we increase the large value of capacitance, okay, like 0.001 picofarad, you can see. Okay, it will not getting the output. Why? Large value of capacitance. Okay, I will again increase the minimize the value. What happens? Let's see. Okay. Okay, it will means from 22 picosecond it will increase 34 picosecond and finally it will increase larger value. You will not get the distorted output. Means as we are increasing the value of load capacitance, our power consumption is also increased and our rise time is also going to be increased. Okay, this effect is very important. Means we have to minimize the load capacitance while designing the circuits or apply. Okay, in this way, ultimately we have designed the. Okay, in this way, what is our conclusion? Conclusion is nothing but we have designed the Cmos and NAND and NOR gate using the MOSFETs, and finally we have simulated and verified using the 120 nanometer technology and assuming the load capacitance. As the load capacitance value is going to be increased, our rise time and power consumption is going to be increased. Okay, and this is the effect of load capacitance, and this is the way how we can design the various CMOS circuit using the microphone software. Thank you.